So in this case, we need to prove the theorem that states that the derivative of e to the x is equal to e to the x for all values of x, all right? Now, in this case, you can begin by defining a function if you like, and say maybe let f of x to be e to the x, or you can use Leibniz notation. That is perfectly fine. And of course, we need to use derivative from first principles. And here we don't need to begin by making any assumption. Why? Well, it's because the natural exponential function is actually continuous throughout, and therefore it's differentiable throughout. Okay? Well, that's fine. So now let's begin. So we can keep it in Leibniz notation, that's okay. And we say the derivative of e to the x from first principles will be the limit as h approaches 0, but it's the limit of what? Of e raised to the x plus h because it's f of x plus h. And then we say minus f of x, which is going to be that. And then we say, well, this is divided by h, okay? And of course, we still need to justify our steps. So we tell them that we actually used the definition of the derivative. That's fine. Then what is the next step? We still have the limit as h approaches 0. Now the question is, how can we evaluate this limit? Well, here you can actually observe something that is interesting. And it's the fact that if you were to go to the first term and you reverse the exponential law and say, before we had exponents adding up, we once had powers of the same basis that were multiplied together. Why would you do that? Well, it's because you can see that both of these terms, they have e to the x in common, and you're trying to access the e to the x from the first term. So that's what you're going to say here. You say I have e to the x, and this is multiplied by e to the h. And then here I have e to the x like that. And then I say, well, this entire thing, it's just going to be divided by h. But the question is, how would you justify this one? Well, you actually reversed an exponential law. So you can say that. Okay. Then where to from this point, we need to factorize. So you have the limit as h approaches 0. And then you say e to the x is the highest common factor. And if you take it out, you are left with e to the h minus 1. And this is divided by h, like that. Then you remember that every time you see an expression like this one, e to the x minus 1 divided by x, but in this case, it has to be h. And you have the limit as h approaches 0. Then you understand this is the limit identity, and it is actually equal to 1. So here you'll just say factorizing. That's fine. And then you can apply the constant times a function rule for limits. So you say e to the x is a constant. And then you times this by the limit as h approaches 0 of e to the h minus 1. And this is divided by h. And of course, you can tell them here that you used the constant times function rule for limits. right? Of course. And then you tell them that, no, you don't need to tell them, but you do need to tell them. So here you have e to the x, which is multiplied by 1. And then you say, well, I recognize that this is the limit identity. And then you can say, this is just going to be equal to e to the x, like that. So now we have shown that the derivative of e to the x is indeed e to the x. Now, what about the next one? Well, this one is asking us to please prove that the derivative of any base, right? It's an exponential function consisting of any ordinary base, any arbitrary base. So we have to show that the derivative of this will be given by a to the power x times the natural log of the base. But this is the problem about this one. Once again, we don't need to make any assumption. It's an exponential function which is defined everywhere in terms of x values. But what is the problem? The problem here is we can't determine the derivative by using first principles. Now the question is why? It's because unlike this one, we don't have the limit identity for any arbitrary base. We only have it for the E base, okay? So the question then is, how can we prove this without using first principles? Because you're going to fail dismally if we do. Of course, you can always try it out. Well, now we are just going to come and write a to the x in a rather intelligent way. Now, what is this intelligent way that I'm talking about? Well, we are simply going to say, okay, fine. I can choose to write a to the x as e raised to the natural log of a. Well, this part is the same as a anyway. It didn't change anything because the function of an inverse is just going to be that. But then you further say everything here is raised to the power x. And what you just used here is actually a property of the logarithms. So you can simply say, well, this is the logarithmic function property. Yes. So these are the properties that you learned as soon as you learned about the inverse functions. As soon as you learned that an inverse of an exponential function is the logarithmic function, then immediately after that you learned those properties. So that's the same property we just applied here. Okay. Then the question is, where to from this point? Well, according to the laws of exponents, if we have b to the n, which is further raised to the m, this is actually b to the m times n. So that's what we are going to say even here. So we multiply these two exponents together, and we simply get e raised to the x times the natural log of a. And of course, we tell them that we are busy messing with exponents, so we can say we used the exponential function property. Okay, that's fine. Then the question is, where to from this point? What was the whole point of doing this? Well, it's because we were trying to generate a composite function so that we can use the chain rule. Remember that when we dealt with limits of the form f of x raised to the g of x. The reason why we had to say, well, this is the same as e raised to the natural log of this entire thing. The reason why we had to say that, it's so that we generate a composite function. This will now be e, which is raised to the g of x times the natural log of f of x. So it's no longer a function raised to another function, but now it's a composite function. Do you see that? But of course, it's not the same reason as, or rather the same thing as what we are doing here, but we have now generated a composite function. That's the whole point of using this. Okay. Then what do we say from this point? Now we use the chain rule to differentiate. So what does the chain rule say? It says you find the derivative of the outside function, which is supposed to be, well, it's not really that. Yeah. It should be that. Because the outside function is e to the x, and the inside function is x ln a, right? So you find the derivative of the outside function, which is supposed to be e to the x, but the chain rule says you keep the inside function as it is, and then you multiply by the derivative of the inside function. So you just applied the chain rule here. All right. Then what do you do from this point? Well, you just differentiate the inside function. So the natural log is just a constant. Remember that. X ln A is the same as having 2x because ln A is a constant, so it's like 2. And what is the derivative of 2x? It's 2. So what is the derivative of x ln A? Well, it's just going to be the ln of A, right? So you times this by the natural log of x. But then how do you justify this step? Well, you tell them that I had to differentiate with respect to x. So this is what you say. And lastly, you're now going to take this and bring it back to what it was before you got that. So in other words, every time you see this, you actually see this exact thing, right? And every time you see that exact thing, you actually see this exact thing. So now you can come and say, okay, fine, where I see e to the x ln a, well, I actually see a to the power x. And then I multiply this with the natural log of a. And once again, you actually used the logarithmic function property. But yes, that is how you are supposed to prove these two theorems for the general case as well as for the natural exponential case.